So we said many problems, mechanical engineering and other engineering discipline will end up resulting in this system. Okay, a system where you have lambda x equal to ax. Okay, an eigenvalue problem. What's our job? To calculate lambda and calculate the x. Solve the system and get its eigenvalue. Alright? So let's do it. Well, here is a matrix 2 by 2, minus 5, 2, 2, minus 2, and he tell you find the eigenvalue and eigenvector. Right? And in the last year in the midterm there was a problem like this. You have a matrix and basically he said, well, calculate the eigenvalue and eigenvector for the matrix. So basically that A is in a system where it's called ax equal lambda x, and we don't know the lambda, we don't know the x. So how we can do this? Well, let's write the equation. So here's minus 5, 2, 2 minus 2, x1, x2, lambda multiplied by the same x1 and x2. Right? Same matrix multiplied by x1, x2 will result in the same x1 and x2 when you multiply by lambda. So basically I can read this equation. It's right, minus 5x1 plus 2x2 equal to lambda x1, and the same thing from the bottom, right? You all can read this, right? So, well, let's put all the x1 in one side and x2 next to them, right? So let's move this lambda here. So actually this will become minus 5x1 minus lambda x1 plus 2x2 equals 0, and 2x1 minus 2x2 minus lambda x2 equals 0. We can actually add those together, right? But I see trouble, right? You see trouble right now? Kind of two equation, and you still want me to get x1, x2 and lambda? It's like two equation and three unknown. So let's pull them together and then we'll see what will happen. So if we just pull the minus 5 and lambda together in terms of x1, okay, and minus 2 and minus lambda together in terms of x2, that's our system that we are solving, correct? That's our system. You can actually think about this system as this is A minus lambda I. What's lambda I? First, what's I? 1, 0, 0, 1. What's lambda I? Lambda I would basically be lambda 0, 0, lambda. That's the diagonal matrix. A scalar diagonal matrix. Right? So this is basically just A minus lambda I. It's as if when you compare it to the original matrix, which is minus 5 and 2 and 2 minus 2, what's the change? The change is in the diagonal. The change that it's all the diagonal element got minus lambda I. Minus lambda basically. Right? That's what's new. So when he said, well, get the eigenvalue for this matrix, it's basically you take this matrix and you say minus 5 minus lambda, minus 2 minus lambda, and then you are basically this multiplied by x equal to 0. That's what you are trying to solve. Solving for lambda and x1 and x2. So one of you should immediately tell me, well, I know the solution. The solution is x1 0 and x2 0. That will do it. But that's the trivial solution. Right? Why it will do it? Because basically you are saying minus 5 x1 minus lambda x1 plus 2x2 equals 0, and minus 2x1 minus 2x2 minus lambda x2 equals 0. Yeah, x1 and x2 equals 0 will solve the system, will give you a solution. But again, that's the trivial solution. Is there is any hope that we get x1 and x2 that's not 0 and 0, that still will solve that system? For a homogeneous system, there is a hope that we can get a solution only if, remember what we started with in the lecture, the end of chapter 7, if the determinant is 0. If the determinant D is 0, then there is hope. we can get a solution that's not 0 and 0. That's not trivial solution, right? So this is just pulled from chapter 7, this slide. Reminding you again, remember in the Kramer method, x1 and x2 was d1 over d and d2 over d, and those d1 and d2 and d3, those were basically the same matrix, but replacing the column with the b vector, the zeros. And so in order to come up with non-trivial solution, the only hope was that this also is 0. Right. So back again to our matrix, that our system that we are trying to solve. We're trying to solve it for non-trivial solution. The only hope that we get non-trivial solution if this determinant, the determinant of this matrix is also 0. Then x1 will be 0 over 0, which is not 0. And x2 will be 0 over 0, which will end up getting a number out of it later. Alright, so basically the determinant of this equal to 0. The determinant of a minus lambda I should be 0. This actually, the determinant of this matrix, that's a number. At the end of the day, that's a number. That's a scalar. It actually will end up, because it has lambda, and we don't know lambda, and we are multiplying lambda by lambda, and you will end up with an equation. Second order equation for 2 by 2, you should expect a third order equation if it's 3 by 3, and so forth and so on, right? This equation, solving it, making sure that this is actually equal to 0, will make the determinant equal 0, will give that system the hope to get a non-trivial solution. Alright? So it turned out that for an eigenvalue problem, to get a non-trivial solution for your x1 and x2, this equation need to be solved. Alright? This is called the characteristic equation. And the solution for it, the lambda value that will do it, that will actually, if you can manage to get lambda value that will make this equal to 0, or make the determinant equal to 0, those are the eigenvalue. Okay? Otherwise, for other value for lambda, guess what? The determinant will end up being not 0, and the solution will be basically just the trivial solution. So this matrix, to have a unique non-trivial solution, you have to make sure that the characteristic equation can be solved, can actually manage to be 0, not 7, not 8. So solving a second order equation is, you should know this, right? The easiest way is to actually turn this into 2 factors if your eye can get it. You know, if you see lambda squared plus 7 lambda plus 6 equal to 0, you should immediately think, well, it must be lambda plus 1 and lambda plus 6, because 6 and 1, that's 6, and if you add 6 and 1, you get 7. Sometimes it's not. So the solution is, of course, if lambda plus 6 equal to 0, that means that lambda is minus 1, or lambda plus 1 equal to 0, that means lambda is minus 1. So it's either minus 6 or minus 1. Those are the 2 values. Because it's second order, you should expect two roots. Right? Just if your eye cannot see it, you know, if the equation is like lambda squared plus 75 lambda plus 154, and your eye cannot tell it, there is any second order equation. Let me put a page here. And this would you remember? This would you need this for the homework, because the equation that will come in the homework is not that easy to actually get the roots. So for any ax squared plus, or let's call it a lambda square, a lambda squared plus b lambda plus c equals 0, where a and b and c are 5 and 7 and 3, or any number, lambda is, does anyone remember? Minus b plus or minus b squared minus 4ac over 2a, where again the a and the b and the c, those numbers are basically the 7 and the minus 1 and the 4 that's here. Okay, that's how you solve the second order that you will get in the homework, right? But in the exam, you know, if the problem is easy and your eye can see it, go for it. Of course, you don't have to do this. Okay, so what we did, we said the determinant need to be 0. Therefore, this, let's get the determinant. It's basically this guy multiplied by this guy minus this guy multiplied by this guy. That's why you will end up with this. Okay, note that, you know, when he see minus 5 minus lambda minus 2 minus lambda, sometime maybe it's useful not to do all the multiplication till the end, but anyway, so he basically get the second order and then he solve for this one and you get the 2 roots. Back again, we just managed to get our 2 roots, our 2 lambda. For each lambda there's a solution, x1 and x2. That solution is called the eigenvector corresponding to that value of lambda. So let's go back here and put lambda equal minus 1. You get minus 5 minus 1, and here you get minus 2 minus minus 1. This new matrix, you solve for x1 and x2 in it. That's what he did over here. So he do it, so this page is basically kind of divided 2 parts. So here is lambda equal minus 1, and here is lambda equal minus 6. For lambda minus 1, here are the new roots, or sorry, the new matrix, and for lambda equal minus 6, here is the new matrix. And what we are solving? We are solving for x1 and x2. Okay? He's doing it by Gauss elimination. You could say, well, I can get it just by, this is 2 by 2. What are you talking about? I can get by substitution. I will just get x1 from the first equation, put it in the second one, and I will get it. Go for it. Yeah, but you know, it's nice when you do Gauss elimination, because sometimes it's basically you get 0 equals 0, and so you remember that, well, so now I have one equation in 2 unknown, and so you immediately recall that when the rank of the matrix get basically shorter, that means that I have infinite number of solution. Right? Remember, one equation in 2 unknown. So he was trying just to get the diagonal number, the pivot, to 0 whatever under. Okay, so you multiply minus 4. How can I get 0 under it? I have to multiply by 2 over minus 4. Actually, minus 2 over minus 4. So it's basically 1 over 2. So you multiply the first row by half and add it to the second. You just find that he had 0, 0 equal 0. One equation, minus 4 x1 plus 2 x2 equals 0. One equation, 2 unknown. Infinite number of solution. For this lambda, there is infinite number of solution. So you choose x1, you get x2. So what x1 will you choose? Don't choose x1 equal minus 0.5732. Okay, just yes, you have infinite number of solution. You have the right, but let's use the principal direction. Let's use. Let's guess 1 or 0 or minus 1 or right. So let's guess. Let's assume x1 equal 1. You get x2 equal 2. Okay, this is a vector that work for this lambda. All right. If I started with minus 1, will I get different number? Yes. And that would be also an eigenvector for this. Alright? So in the homework this week, I'm basically telling you, you can get the lambda by yourself, right? But you can have a lot of vectors. So I was actually in the homework, I'm saying, prove that the eigenvalue is this, and the eigenvector is that. So to get the eigenvector that I want, you will just have to find what is the right x1 that you will assume, so that you can get the same vector that I have. And it's not going to be minus 0.5783. So it'll probably be either 1 or 0 or minus 1. You had a question. What's your name again? Matthew.
Doing something different when you plug in the lambda, because our equation.
Let's check. So you're saying when we put the lambda equal minus 1, the matrix look a little bit different.
Oh, I see. I wrote it down.
So it's minus 5. Remember, minus 1.
Yeah.
So you'll end up with minus 5 plus 1.
I had it written down.
Alright. So you'll end up with the minus 4. On the other side, same process exactly. Let's just do it for fun. So lambda 2 equal minus 6. That's the next value we came up with from the characteristic equation. You put it, this minus 6, you put it here, okay, and what you get? You get minus 5 minus, sorry, minus 5 minus minus 6. Obviously you'll get 1 on this diagonal. 1, 2, 2, and then minus 2 minus minus 6. That's minus 2 plus 6. So you'll get the 4. So you'll get the 1 and 4, 2 and 2. Here's again 2 equation, 2 unknown. We are solving it by Gauss elimination. We are taking this, zeroing under it. Same story, you get a line of zeros. Infinite, 1 equation, 2 unknown, infinite number of solutions. Right? So choose x1, you get x2. So let x2 equal minus 1, you get x1 equal 2. Alright? If you choose x2 equal 1, will you get different thing? Yeah, you will get another value. Questions? So the whole eigenvalue problem, the key to solving it is to realizing this, that the matrix that will show up is actually now A minus lambda I. Okay? A minus lambda I multiplied by x equal to 0. Homogeneous system, the only way to get non-trivial solution is that if A minus lambda I has a determinant equal to 0. That is the characteristic equation. Right? So solving this problem is basically to put your hand on that characteristic equation, solving the characteristic equation, whether it's second order or even worse third order, you solve it, and you substitute those lambda value back again into the system and get the vectors. Okay? Anything difficult about this?
So the final answer would be your eigenvector?
And the eigenvalue. So the final answer would be the eigenvalue and the corresponding eigenvector to it. The difficulty would be solving the second or third order equation that will come here. If it's third order, then it's hard to solve. Not that easy, right? And a lot of students also don't get this right to start with. They don't put their hand on the characteristic equation. I mean, they have the A, but then how do you turn this A into an equation? And the secret is you just put minus lambda on the diagonal. You just basically all the diagonal element, you add to them minus lambda, minus lambda, minus lambda, and you calculate the determinant. Set it equal to 0. Those are the steps. You get it? Let's do it one more time, and you will do it in the homework. So this is by, you know, for n system, n equation in n unknown, same procedure exactly. Alright, so the eigenvalue problem is that this A, which is n by n multiplied by the x, is lambda multiplied by the same x. And the question we are trying to answer is what is the lambda that will do this and what's the x that will result in it. Alright? And so where did this come from? You know, just, I mean, take this guy and send it this way. You will end up with ax minus lambda x equal to 0. Or simply just a minus lambda I x equals 0. And so homogeneous system, the only way for it to have non-trivial solution is that if the determinant of this multiplied by x, this guy, this new matrix, it's not a, it's a minus lambda I. Look at that. All the diagonal of the a, original a, now have just minus lambda, minus lambda, minus lambda all the way. And this determinant need to be equal to 0. The determinant of this new matrix, determinant of this need to be equal to 0. So if it's 2 by 2, it's easy, but 3 and 3, the matrix is bigger, and the determinant will just basically what we did in the quiz, you know, plus, minus, plus, and you just use, well, pick a row that's easy to, it doesn't matter which row you solve, right? You open the matrix that determinant with. Just pick the row or the column that you like. That makes sense. And so he's basically saying over here that the eigenvalue of a square matrix A are the roots of the characteristic equation that will come, and n by n matrix will have at least one eigenvalue and at most n. numerically different value. So you could actually have a 3 by 3 will result in lambda 1, lambda 2, lambda 3. All of them is basically just 1. Not same number. They could basically, that's okay. Alright? So let's see this one. So that's example 2 in our book. So minus 2, 2, minus 3, 2, 1, minus 6, minus 1, minus 2, and 0. Alright? So he want the eigen. Here's the question will look like this. Calculate the eigenvalue, calculate the eigenvector of the thing. So you basically say, well, a minus lambda I x equal to 0. Therefore, I need that a minus lambda I, and look at, I'm doing the determinant by doing this, should be equal to 0. Right? What is this new matrix that has not just a, it's a minus lambda I, it's the same as a except minus lambda, 2 minus 3, 2, 1 minus lambda, minus 6, and minus 1, minus 2, and minus lambda. See, it's this determinant that now need to be equal to 0. Or a cleaner version is basically in front of us over here. And you can see the changes is basically, it's just those lambda that we add on the diagonal. Alright? And this is a determinant now, not a matrix. So a matrix you make it like this, but determinant you basically just put this. And you'd say this need to be equal to 0. And let's open it 3 by 3. Alright? So the fun start when you actually open this guy. So he's opening it from this and this and this. So you can see the minus 2 minus lambda, and here is this minus 2 over here, and here is the minus 3 over here. Okay, and what is that? That's the small matrix, that the determinant of the small matrix that will remain. 1 minus lambda multiplied by minus lambda minus 6 times minus 2, or basically minus 12. Okay, so this will result in a second order, but there is a bracket next to it. Alright, and this is the other two guys. So as expected, you know, if it's 3 by 3, you should expect a third order, right? Because there is lambda, lambda, lambda 3 times. So good luck solving this third order. If you are lucky, you can basically immediately see that with this 45 is, you know, can be divided into basically maybe 9 times 5, and this 9 times 5 can basically be 3 times 3 times 5, and then you basically write it like this, and so that's the solution. So obviously lambda is minus 3 and 5. What if your eye cannot see it? So we will spend in chapter 19 a lot of time on different methods for non-linear equation. This is a non-linear equation because lambda is to the power 3. Okay, so the easiest way is that you can plot it in your calculator, right? If you can plot it in your calculator, you will basically be able to see that it's probably, it will hit basically at two places, minus 3 and the 9, for example. You can actually see when it will become 0, and so those are the roots. Another way that it's very easy done on your calculator too is that you just pull one of those lambda on the other side of the equation. So there are 3 ways you can do this. You can pull this lambda or that lambda on this lambda, right? If you pull this one, it will be the square root of whatever go to the other side. If you pull this one, that's easy. This is basically just everything here divided by the 21. You just pull one lambda out of this and put it on the other side. So what happened then? what happened then is that basically this would be a formula, a recurrence formula to calculate lambda. So if you store this in your calculator, this equation in your calculator, so that anytime you hit the calculator, he give you the value of this right hand side or this formula, all you have to do is just change the value of lambda. And basically you actually use the previous value. So you assume 3, you calculate something, you take that something and you calculate one more value of it. And if the problem will converge, you find that eventually you put lambda and you get exactly the same lambda. So what does this mean? That means you found a solution. So what are you trying to do again? We are trying to find a lambda that will make this equal to 0. So when we pushed lambda, we move one of those lambda to the other side. Now the equation is not this equal to 0. Now the equation is this side should be equal to lambda. So the fact that you substituted lambda in this formula and you get exactly the same lambda, that means that it satisfies the original equation. Alright? We'll spend more time on this again in chapter 9. But basically I am telling you that if you set the equation in that form and you just basically just keep feeding the number to the same formula, whatever the formula calculates, you basically let it run again with the same number. Eventually it will converge if it's in a conversion mode. Alright? And so you will basically get the solution. So the solution here is 5. Right? Sometime it converges, but it converges really slowly. That it doesn't really work that way. Alright? And there are more sophisticated methods, like Newton-Raphson method, and we'll talk about again, but it basically involves writing the equation as function and differentiating this function, which is nothing because that's a polynomial. What's the differentiation of lambda squared? Lambda cubed, 3 lambda squared. What's the differentiation of lambda squared? 2 lambda. What's the differentiation of minus 21 lambda? Minus 21. 45, that's 0. So getting this and this, that's really easy. And then the formula is basically to get the root is this. Okay. This is what you're trying to find out. This is the initial guess. Right? So the new value that you are trying to say it's a good approximation of the root, or basically I'm hoping it's the root eventually, is the old value multiplied by basically this divided by this. Right? So we can write the formula. For you it's basically simply xn plus 1 minus xn is equal to minus fxn divided by f prime xn. Right? That's what's plotted over here. So for any initial guess xn, you calculate fx and you calculate f prime xn. What's that? That's the f and that's the f prime. So see, you start here with minus 2, you calculate the f and you calculate the f prime. And this formula over here is simply xn minus f over f prime. Again, fn over f prime n. Okay, well, maybe it's not really good for a calculator, but over an Excel file, it's a piece of cake. You write this formula just for one line, and then you build the whole line down, and you can see that basically the root converge to 3. So you put 3 and you get 3. Alright? Fortunately for you, in your homework today, that there will be an equation, characteristic equation that you need to solve to come up with the eigenvalue. But it does not require iteration, because actually it's in symbols. So the solution is the matrix is basically cosine theta and sine theta, and and we don't know what theta is, so there is no numbers, it's all symbols basically, right? And he actually would like you to prove that the eigenvalue is e to power I theta. I'll show you the homework in a second. But anyway, so those are the some ways to basically solve eventually the characteristic equation. Alright, and again we will spend chapter 19 talking about those different methods. Question about this so far? Alright. So he found basically the eigenvalue lambda 1 and lambda 2. Okay, note that this particular equation that we are solving will end up with two roots that's exactly the same. So it's just minus 3 and plus 5. So two of the roots are basically exactly the same value. So what happened next? We basically put lambda 5 and lambda minus 3. We plug them into the matrix A minus lambda I, and now we will solve for the eigenvector. How do we solve it? We turn it into basically use Gauss elimination to try to turn it into an upper triangular matrix. So what he will do, he will use this minus 7 to get 0 here and 0 here. He did it, 0 and 0, but in the process, note that when we use Gauss elimination, do you remember there's something missing here? What's missing? Huh? Right, the other side. Remember we used to put this line and then we have to put the B. Why he's not yet doing it? Because it's a homogeneous system, and so no matter what he multiply this number, this 0 with, and adding it to the next one, nothing really will change. Say sure, go and carry the 0 all the way, but you look silly. Alright? But that's the proper way to do it, the Gauss elimination. I mean, you just keep moving them. It also could help you, eventually at the end when you get this line of 0, you may get lost, like what? 0, 0, 0, but if you have a 0 over here, it's equal to 0, then we are okay. Anyway, so he do it for basically both sides. So this one he will get zeros, and in this side he get, right, so 2 equations, 3 unknown, 1 equation, 3 unknown. Infinite, infinite. But here we will have to guess one guy, and we will get the other one, right? But over there on the other side, we will have to guess 2 of them, right? If you have 1 equation and 3 unknown, x1, actually let's read it. What this equation say? Say x1 plus 2x2 minus 3x3 equal to 0. So, or simply, I mean, let's put x1 in one side and let's take those 2 guys on the other side. So it would read this. It would read x1 equal to minus 2x2 plus 3x3. So the only way to come up with x1 is to actually not just assume x2 but also assume x3. Alright? So on this side of he assume x3 minus 1 and he get x2 equal 2, and then he get x1 equal 1. How he doing this? Because he can get x2 from this equation, and then once he get x1, once he get x2, then he go to this one and get x1. Let's do this slowly. So in the second equation, it's basically reading minus 24 over 7, and there is a reason why he didn't do the division. Easy in the calculator to do 24 over 7, but in the digits you start losing the accuracy. So if you can keep the fraction, it's nice, because eventually we assume 1 and zeros and stuff, so you can get the solution pretty quickly. So it's minus 24 over 7x2 plus minus 48 over 7 x3 equals 0. That's this one. And the first one, it's basically saying minus 7x1 plus 2x2 minus 3x3 equal to 0. Alright? So when he assumed x3 minus 1, it's obviously that this guy is basically half this. So he can really see that x2 is 2. So what I'm trying to say, if he had done if you, in solving this, you already did the fraction and then it's 0.666, huh? And you multiply by 2, you may not get really x2 equal 2, you may get x2 equal 1.99999, right? And it's not really accurate. It should have been 2. So keeping the fraction is more accurate. Alright? So setting this guy equal to minus 1, you will be able to get this equal to 2. And then coming here and setting this to minus 1 and this guy equal to 2, you can easily get x1 equal to 1. Okay? Because it will be 4 plus 3. So 4 plus 3, that must be 7. Minus 7 and 7, you will get the 1. Right? And look at the way he wrote x1. You see why he having this transpose on top of it? To save space, basically. So rather than, because it's x1, x2, it's a vector x1, x2, and x3. So to just make it in one line, he's basically telling you is the transpose of that row. It's a column. Alright? So now, on the other side, that's what he end up with. Alright? And so again, he will have to choose the value for x2 and x3. He will actually have to choose not once. Look at that. He chooses it twice. Why? Because he got 2 lambda for this side. Lambda equal 3, lambda equal minus 3, and lambda equal minus 3. So he is entitled to get 2 independent eigenvector for that value. Alright? So 1 and 0 and 0 and 1, those are, 1 and 0, that's this guy, and 0 and 1 is that guy. Right? So they are not really a version of each other. Those are completely independent, linear independent vectors. Alright? So he assumed x2 and x3 here and here, here and here. He assumed x2 and x3, and he get x1 corresponding to it. Alright? So for basically 0 and 1 he get minus 2, and for 1 and 0 he gets 3. I'm talking about x1. So this will give you x1 equal to minus 2, and this will give you x1 equal to 3. Alright? And so here are the 3 eigenvector. And when you say x1, see that x is still a vector. So x1 is basically, it's like, it has the 3 components that he's solving them. So whether his dimension basically, we don't know what is the vector that he was solving this over it. Maybe it's y1, y2, and y3. Okay? What I'm trying to say is that those eigenvector, they basically have the solution for x1, x2, and x3. Or whatever the variable name that he's solving the matrix for. Questions? Alright. So one more thing that's important here is symmetric and skew symmetric and orthogonal matrices. Right? So a symmetric matrix, we know that, right? That's the one that we knew. What is symmetric matrix? There is this symmetry across the diagonal. So when you transpose this matrix, basically you end up exactly with the same. Remember transposing, turning Aij to Aji? Right? So the rows become column and the column become rows. And the skew symmetric, that's basically when you transpose, you get the minus A. So for this to happen, first, yes, the diagonal need to be 0, but so this way Aij become minus Agi, The only way is that if the diagonals are 0. That is a skew symmetric. And on top of that, across from the diagonal, things have negative sign. So 20 minus 20, 12 minus 12. This is just the terminology. That's the what a skew matrix, skew symmetric matrix, and what a symmetric matrix is. Okay? Why those are important, we'll see in a second. And there is this one, orthogonal matrix. So orthogonal matrix is that when you transpose that matrix, you will end up with its inverse. So the transpose of the matrix is the inverse of the matrix. Wouldn't that be nice? All you have to do to get the inverse, you just basically flip the rows of the column and you have your inverse. The matrix inverse. So over here, he's saying that the eigenvalue of a symmetric matrix are real. So they cannot be imaginary. Right? And the eigenvalue of a skew symmetric matrix are imaginary or 0. Okay? And the other important thing is that any real square matrix can be written as the sum of two matrices. One of them is symmetric and the other one is skew symmetric. So any A, where A is real matrix, can be written as the sum of R and S. If you add those R and S, you'll get the A. What are those R and S? One of them is symmetric and the other one is, look at this. This one is symmetric, right? Minus 2, minus 2, 3, 5, 3, 5. And this one is skew symmetric. The sign are flipped across the diagonal and the diagonal is 0. Not only that, A is R plus S, but he also gave you R and S. Here is R and here is S. Okay, that's the R, the symmetric matrix, is A plus A transpose, and the skew symmetric is A minus A transpose. Half multiplied by half multiplied by half. Right? So you can basically kind of decompose the A into this basically summation of R plus S this way, using its transpose. Alright? Questions? Those will prove useful in the due time. Alright, the last thing actually on this, and then we'll do the homework, is the determinant of an orthogonal matrix is +1 or -1. What's the orthogonal matrix? Well, it's this one that when we transpose, basically you get the inverse. Okay, so he's saying that the determinant should be 1 or -1. So here is the proof. Here is the determinant of that A. The A is the orthogonal matrix. Alright? So he proved it basically by going backward. To start with, remember determinant AB is determinant A multiplied by determinant B. Okay, so he want to prove that this is equal to 1 or -1. The fact that determinant A square is 1, when I'm telling you that x square is 1, that means that x is either 1 or x is -1. That's the only way. Okay, so 1, that's the determinant of a diagonal of the unity matrix I. And because A is orthogonal, A multiplied by A -1. Actually, no, because A is just A. Any A multiplied by A -1 is I. And because A is orthogonal, A -1 is A transpose. Alright? And the determinant of this guy is the determinant of A multiplied by the determinant of A transpose. Alright? And doing the transpose of a matrix does not change its determinant, because rather than opening with the row, we can open with the column. So doing the transpose on a matrix does not change the determinant. Right? So this is exactly the determinant of A multiplied by the determinant of A. The determinant of A multiplied by the determinant of A, or determinant of A square. So you prove that the determinant of A square is 1 as long as A minus 1 is A transpose, or basically it's orthogonal matrix. You got it? Questions about this? Right, so this could like be prove something in the exam, you know, and you can basically, using this rule, you can prove certain rule like that.